Hello people, today we are going to do an experiment to see if it is possible to send information in a superluminal way, that is, at a speed greater than that of light, using quantum entangled qubits. In a previous video we saw that a pair of quantum entangled qubits communicate with each other instantaneously. So one could think if it is not possible to use this phenomenon of quantum entanglement between qubits to transmit information and communicate from two very distant places at a speed greater than that of light, that is, at a speed greater than what we could do for any other signal of radio or television. Suppose, for example, that Anna and Bob share a quantum entangled pair of qubits. Anna is going to travel to Pluto and Beto is a journalist and stays here on Earth. So he wants to have the scoop so that when Anna gets to Pluto, she will tell him if there is life on Pluto or not, and he wants to have the scoop to have it before anyone else. Beto and Anna agree so that when she gets to Pluto will put its entangled pair qubit in state 0 if there is no life and 1 if there is life. Beto's qubit will then instantly go to state 0 or 1, that's what they think. A second later, Beto is going to read his entangled pair qubit and will know immediately if there is life or not on Pluto, and he publishes the scoop before anyone else. The synchronization of the clocks has another additional problem. But let's think that Bob and Anna's clocks are perfectly synchronized. Anna knows exactly the day and time that she is going to arrive at Pluto. At that moment it will put its entangled pair qubit in state 0 or 1. A second later Bob read his entangled pair qubit and immediately published the news to get the scoop. Well, we are going to do the experiment on the IBM quantum computer and we are going to see if this is possible or not. To begin, we are going to enter the IBM quantum computer with our email address and password. Well, now within the quantum computing environment, the graphical environment, we are going to build a quantum circuit putting the two qubits in an entangled state. For that we initially have the two qubits at 0, we are going to use an atomar H gate on the qubit Q0 and an F node control from Q0 to Q1 to put the two qubits Q0 and Q1 in an entangled state. The two states are 0, 0 with a probability of 50% and 1, 1 with probability of 50% as well. Of these two qubits, Anna takes Q0 and Beto keeps qubit Q1. Look here, very important, these little circles that you see here have a small black circle inside that indicates that the two qubits are in an entangled state and with probability 50 and 50 of each being in state 0 or 1. When Anna reaches Pluto, then she has to transmit information 0 or 1 to Beto. Suppose there is no life on Pluto, so what Anna does is reset her qubit. This gate is a reset gate that sets qubit Q0 to 0. But look what happened as soon as Anna reset her qubit. The entanglement disappeared. That little circle that we had in here before disappears. That is, the entanglement is lost. Now we are going to continue with the process. Anna then reads her qubit and a second later Beto reads his. This is the process. We run it on the quantum computer. We're going to select IBM Q Lima and we're going to see what we get. A few moments later, then we already have the circuit executed, the quantum computer, and we are going to see what we obtained. Notice that the states read are 0. Here the computer repeats the experiment 1024 times and obtains the corresponding statistics 543 times read 0, 452 times read 10. There are other results that are erroneous due to the uncertainty associated with quantum systems. The states obtained are mostly 0 and 10, that is, Anna's qubit is in state 0, it is the one with the least weight. But Beto's qubit is approximately half of the times at 0 and half of the times it is read in 1 per. Therefore, when Beto actually reads, he does not know if Anna actually sent him a 0 or not because he will read a 0 half of the time and a 1 half of the time. That is, his qubit is no longer intertwined with Anna's qubit but has a qubit in equiprobable superposition state. Now let's go back to the case where there is life on Pluto. Then Anna has to send a 1. What does it do? Well, after it sets its qubit to 0, look, I'm going to insert a NOT gate here because this makes the ANA qubit reset it and then sets it to 1. Here it is at 0, it applies a NOT gate, sets it to 1, reads it, and a second later beta reads it. But notice that exactly the same thing is happening. Now 50% of the time this system will be in state 0, 1, and another 50% in state 1, 1. Anna's qubit is the one with the least weight. It is always at 1, because she put it at 1, but Beto's is not always at 1. Sometimes it is at 0, sometimes it is at 1. We are also going to run it on the quantum computer. We are now going to choose IVM Qubellion. We run it and we are going to see what we get. Well, here we have the result. Here we have the result. We have the most probable states 0, 1 and now 1, 1 indeed. The qubit with the least weight, Anna's, is at 1 with maximum probability of these two most probable states, but the qubit de Beto returns to either 0 or 1 approximately half the time for each case. These other two readings are typical of the uncertainty associated with quantum computers. But again, Bob, no matter how much Anna has set the qubit to 1, she is left with a qubit in a superposition state that can either read 0 or 1. So that in neither of the two cases can Anna set 0 as much, or in 1 its entangled pair qubit Beto in either of the two cases is going to have a qubit in a superposition state with the same probability of reading 0 as of reading 1. Therefore Anna could not send any information to him at a speed greater than the of light, taking advantage of the quantum entanglement of this entangled pair of qubits. Why? Because at the very instant that she applied the first gate, the reset gate on her entangled pair qubit, the entanglement state was lost. Well folks, I hope you're not too disappointed to find out that superlight communication is impossible, at least with quantum entangled qubits. Well, I hope you liked the video and see you in the next one.